Hey, today I'm going to read the Chapter 11 slides for Meteorology and Atmosphere. This chapter is about hurricanes. Alright, what is a tropical cyclone? A tropical cyclone is a low-pressure system that originated in a tropical region, which is between the tropics, 23.5 degrees north and south, and excluding 0 to 5 degrees north and south due to the Coriolis force, because there's no Coriolis force at the equator, from the equator to 5 degrees north and south. Tropical cyclones form over warm water. They have organized circulation. Their main energy source is the release of latent heat. And the most intense tropical cyclones are known as hurricanes or typhoons, depending on their region. Because there are different names for hurricanes around the world. Ingredients for tropical cyclone development. Warm water temperatures of at least 80 degrees Fahrenheit or 26.5 degrees Celsius, or warmer to a depth of at least 150 feet. Oh, don't mind that, that's the printer. Rapid cooling of rising, unstable air. That's another ingredient. The next ingredient is high humidity in the lower to mid-troposphere. It needs a weather disturbance, for example, an easterly wave as a starting point. And weak upper-level winds, little wind shear, because the wind shear breaks up the clouds at the top. So wind shear actually prevents it from forming as well. There's a picture here of the inside of the layers of a cyclone. So it's got the eye of the cyclone and all of the layers that are broken up into different walls. I'm not sure how to describe the hurricane exactly, except that it has the eye in the center, which has the eye is the calmest part of the storm. And then it has the eye wall, which surrounds the eye. And then it has like these chambers in between these surrounding layers of cloud walls. At least that's what it looks like on the picture here. So I'm going to read the little bubbles that talk about the components of the hurricane. We've got deep low pressure, which is deep central low pressure that draws surface air in from all directions. There's sea spray, which is rapid air inflow that whips up huge, frothy ocean waves, and sea spray, which evaporates and increases the moisture content of the air, which helps to strengthen the storm. Then there's latent heat, which is inflowing air when inflowing air reaches the eye wall. As it rises, it cools to the dew point, and water vapor condenses. This condensation releases latent heat. And then finally, unstable air. Latent heat increases the instability of the rising air. This deepens the surface level low pressure as air rises faster. And then it says go back to number 1, which is deep low pressure. I think that means it repeats that cycle again. From deep low pressure, sea spray, latent heat, and unstable air. Tropical cyclone basins and naming convention. So, in the North Atlantic and Eastern Pacific, hurricanes are called hurricanes. In the Northwestern Pacific, it's called a typhoon. In Australia, or the South Pacific, it's called a willy willy or a boggio. And in the Indian Ocean, it's called a cyclone. Tropical cyclone basin formations. There are 7 tropical cyclone basins where tropical cyclones form on a regular basis. In the Atlantic Ocean, or the Atlantic Basin is in the North Atlantic Ocean, the Gulf, and the Caribbean Sea. Here, the hurricane season is officially from the 1st of June to the 30th of November. Peak activity is in early to mid-September. Once in a few years, there may be a tropical cyclone occurring in May or December. The Northeast Pacific Basin is from Mexico to about the dateline. This has a broad peak with activity beginning in late May or early June and going until late October or early November, with a peak in storminess in late August and early September. The Northwest Pacific Basin goes from the dateline to Asia, including the South China Sea. This is where tropical cyclones occur all year round, regularly, though there is a distinct minimum in February and the first half of March. The main season goes from July to November, with a peak in late August to early September. The North Indian Basin includes the Bay of Bengal and the Arabian Sea. It has a double peak of activity in May and November, though tropical cyclones are seen from April to December. The severe cyclonic storms, which are greater than 74 miles per hour or 119 km/h winds, which occur almost exclusively from April to June and again in late September to early December. The Southwest Indian Basin goes from Africa to about 100 degrees east. Beginning in late October to early November, reaching a double peak in activity, one in mid-January and one in mid-February to early March, and ending in May. The Southeast Indian Australian Basin goes from 100 degrees east to 142 degrees east. Beginning in late October to early November, reaching a double peak in activity, one in mid-January and one in mid-February to early March, and then ending in May. Kind of like the one we just covered, the Southwest Indian Basin. But the lull in February for the Australian Southeast Indian Basin is a bit more pronounced than the Southwest. Finally, there's the Australian Southwest Pacific Basin that goes from 142 east to about 120 west. It begins in late October to early November, and reaches a single peak in late February to early March, and then fades out in early May. So it seems like those last three kind of have a similar schedule with some differences in strength and timing. Tropical cyclone basin formations. Okay, there's a picture here, and it has hurricanes around the world and their season dates. So we've got hurricanes from August to October, typhoons from June to December, cyclones from January to March. Now, hurricanes and typhoons, it varies a little bit by location. So the Gulf Hurricane Basin, it says from August to October, but the Pacific Hurricane Basin is from June to October. So just a couple months difference, but depending on which ocean the hurricane is from, it's either August to October or June to October. For a typhoon, if it's in the Pacific, it goes from June to December, and if it's on the other side near the Indian Ocean, it goes from June to November. Stages of hurricane development. The first stage is the tropical wave. This usually originates from North Africa and moves westward. It's referred to as easterly waves, and it's characterized by elongated areas of low pressure. It can cause thunderstorms. It's oriented north to south, and it originates in the ITCZ between 10 and 25 degrees north in latitudes. There are a couple pictures here that show One, the easterly waves and how they move with convergence and divergence. The upper air winds go up and over this little, almost like a little mountain ridge, but it's in the air. And then the other picture has an example of how water moves in the sky. So you've got the ocean air, which evaporates up and makes the air moist. You've got precipitation, and that creates these thunderstorms. Then you've got the dry air coming down. The second stage of hurricane development is a tropical depression, which is a low-pressure system that starts to form, and you can, on a map, it looks like an enclosed isobar. It has organized circulation in the center of the thunderstorm, and central pressure begins to drop rapidly. Wind speeds, though, still remain below 39 miles per hour. The third stage of hurricane development is a tropical storm. Pressure continues to fall. The system becomes more organized and circular. Rotation begins to show an eye, which is going to be in the center, remember. Wind speeds are between 39 miles per hour and 73 miles per hour, and the system is assigned a name. So it begins to be known as Tropical Storm Isaac instead of Tropical Depression 10. And then the fourth stage of hurricane development is a hurricane. It has winds of 74 miles per hour or greater, and 5 categories based on wind speed. And it's measured, the wind speed is measured on the Saffir-Simpson Hurricane Wind Scale. A tropical depression is between 37 and 63 kilometers an hour, or 23 to 38 miles per hour. A tropical storm is 64 to 118 kilometers an hour, or 39 to 73 miles per hour. A Category 1 hurricane is greater than 119 to 153 kilometers an hour, or 74 to 95 miles per hour. A Category 2 is 154 to 177 kilometers an hour, or 96 to 110 miles per hour. A Category 3 is 178 to 208 kilometers an hour, or 111 to 129 miles an hour. A Category 4 is 209 to 255 kilometers an hour, or which is equal to 130 to 156 miles an hour. And a Category 5 hurricane, which is the most destructive, is 252 kilometers an hour to 157 miles an hour. So those last three are the major hurricanes: a Cat 3, Cat 4, and Cat 5. I'm not going to read off the anticipated storm surge levels for each one, but you can look at those on the slides. How do we measure tropical cyclones? Okay. So I've looked in the book to see what it's called. The little device with a instrument package. It's called a dropsonde, and it's a cylindrical instrument package that is dropped from an aircraft and falls through the storm with a parachute, which reads all of the measurements of temperature, pressure, winds, and humidity. The next slide shows the stages of hurricane development, but in a complete picture. So it starts out as a tropical wave with a mass of thunderstorms that forms that sort of wavy pattern in the wind. Next is the tropical depression, where winds increase and a closed rotation begins because of the Coriolis force. Next is a tropical storm, where winds exceed 63 kilometers an hour, or 39 miles per hour, and the storm begins to become organized. This is where it gets a name. And finally, a hurricane, where winds exceed 119 kilometers an hour, or 74 miles per hour, and there's strongly closed rotation with well-defined rain bands. And you can see how it begins to build in the picture. Hurricane naming conventions. Hurricane naming conventions in the North Atlantic. Female names were given to Atlantic hurricanes, really tropical storms, beginning in 1953. Male names were added in 1979 by the World Meteorological Organization. And 6 name lists are rotated every so many years, every 6 years. So 2019 names will be used again in 2025, but names will be retired if the storm is especially traumatic and destructive, so that it doesn't remind people of the previous storm from the last decade or so. I'm going to skip the list of names because that's really long, but there is a list of names from 2025 to 2030 that you can check out. Distribution and paths of tropical cyclones. They start in the tropics with warm, moist air and move west within belts of trade winds. They turn as they enter the zones of the westerlies. So there are fewer in the southern hemisphere and none along the equator because there's no Coriolis effect. Tropical cyclone structure. What is the structure of a tropical cyclone? 1. Spiral rain bands, which have dense cirrus overcast and low central pressure. 2. An eye, which is characterized by a cloudless area at the center it has calm weather, and the size averages between 20 and 40 miles in diameter. And then there's the eye wall, which is located around the eye and has the strongest winds. So a lot of people are fooled by the eye because it's calm. They think that the storm has passed by, and then they get hit by the eye wall, which is even stronger than the previous bands of the storm. Profile of a tropical cyclone. There's some pictures here. One shows a hurricane. One shows, I believe that's pressures, although it's kind of hard to see, so I'm going to skip that. And the final picture is another example of the inside of a hurricane. So we've got the eye that pulls air downward, which is a little different than your typical, it's still a low pressure, but instead of the air rising up like a low pressure typically does, it pulls the air down in the eye. So in this picture you can see the eye with pulling wind down, and you can also see spiral rain bands. There are easterly trade winds. There's surface convergence and divergence aloft with high altitude winds. The profile of a tropical cyclone again has an eye in the middle with an eye wall, and the eye wall clouds come up and then they hit the troposphere, and there's inversion. Similar to what you see with an anvil cloud, where it comes up and then it starts to go sideways in the sky because it has reached the troposphere. And the inversion spreads it out across the air aloft. Then there are rain bands past the eye wall that radiate out in layers. And then there are 3 charts with surface air pressure, surface wind speed, and rainfall intensity in correlation with this picture. So the strongest pressure gradient is right along the eye wall in this picture. Actually, I will let you look at the charts because it's very visual and I don't think I can do it service by trying to explain it all. But each of these charts corresponds with the eye wall. And you can see the rise and fall of pressure, wind speed, and rainfall intensity between each layer. I'm going to skip the 10 deadliest hurricanes to strike the continental US page because it's a very long list and it might be better to look at it. Storm tracks start off going east and are impacted by the westerlies. So we have a picture here of several famous hurricanes and the paths they took. They took the usual path of crossing over the Gulf, and then as they turn upward into the United States, they get hit by the westerlies. So what you see in the chart here is this curve. What affects the strength of tropical cyclones? Changes in water temperature, because warm water strengthens and cold water weakens. A tropical cyclone. When a tropical cyclone encounters air masses, because moist air strengthens and dry air weakens. When it encounters land, because land weakens, especially mountains. And increased vertical shear, because wind shear weakens, it spreads out the latent heat. And it tears up the upper clouds. Damages with tropical cyclones. So there's high winds, flooding, tornadoes, and heavy rainfall. Damages with tropical cyclones. A coastal storm surge is the most dangerous aspect of a tropical cyclone. So storm surge is a rise in sea level caused by strong winds and low atmospheric pressure of a hurricane. The Indian Ocean is particularly vulnerable because large populations live near the coast, and poverty makes evacuation difficult. Storm surge factors. The geometry of coast. Gentle slope and shallow water equals greater storm surge. Concave coasts and narrow bays equals higher storm surge. Storm category. So the first storm surge factor is geometry of coast, and the second storm surge factor is the storm category. So generally speaking, a high category, lower central pressure will equal a higher surge, where weak storms with a vast wind field can create still high storm surge. A third factor of storm surge is the tidal stage. So high tide equals higher storm surge. And if you have a high tide, you're more likely to, the storm surge is more likely to rise over a slope. So normally, if the storm hits at low tide, a slope in the land might keep the water from going too far up the coast, but high tide will make it more severe, and it's more likely to rise up and over a dune or even storm walls. It's more likely to go up and over and much higher. Low pressure and wind form a mound of water that is pushed on shore, which floods low-lying coastal areas. And you can see a little diagram here with a sloping beach with water where at normal high tide it would be 2 feet up the beach, but with storm surge it's 15 feet or or 17 feet. Storm motion and quadrant winds. So in this picture you can see a series of arrows going around a hurricane, and that's because different sides of the hurricane have stronger and weaker winds. So the north and south side of the storm has 100-degree winds, let's say. The right quadrant has an additional 20 degrees of wind, and the left quadrant has a decreased by 20-degree winds. And by degrees, I mean miles per hour. So the right quadrant is stronger, the left quadrant is weaker. And the upper and lower quadrants, those north and south quadrants, in this example, they're 100 miles per hour. From south to east, from east to north, from north to west. It would go from south to east and increase in strength. It would go from east to north and decrease in strength by 20. And then from north to west, it would decrease another 20. So it would be 100, 120, 100, and then 80. Different quadrants of a hurricane equal different hazards and disasters. So there's a visual slide here, and basically what it's saying is that you will have different hazards depending on which side of the storm hits land, because if you remember, the right side of the right quadrant is stronger than the left side. So you will have less damage on the weaker side of the storm than on the stronger side of the storm. So it matters how the hurricane hits land. Tracking tropical storms. There's a picture here of Tropical Storm Dean, and it shows let me look at my notes real quick to see what that's called. It's called a forecast cone because they used to be cone-shaped, and then they sort of rounded them off visually over time. But here in this picture we've got Tropical Storm Dean with a forecast cone that starts out in the Atlantic and starts to come up toward the Gulf. And we've got one more slide here. Hurricane watch and warning. So a tropical storm watch is issued when tropical storm conditions are likely to threaten an area within 48 hours. A tropical storm warning is when tropical storm conditions are expected within 36 hours or less. A hurricane watch is issued when hurricane conditions and related hazards are likely to threaten an area within 48 hours. And a hurricane warning is issued when hurricane conditions and related hazards are expected within 36 hours or less. So this is kind of similar to tornadoes, but different in the sense that tropical storms and hurricanes are a little more observable. You see them coming for a longer time and you can see their trajectory. So instead of just being based on, a tornado is based on the factors of, are conditions favorable and has a tornado actually been seen? That's the difference between a watch and a warning for a tornado. Where for hurricanes, you can see the hurricane is there. You can also predict where it's going to go. You can see its trajectory. You can see all of the factors that will influence where it's going to go. So you can predict how fast it's moving, when it will threaten an area. So instead of being just, is it there, isn't it there, it's more a matter of, when is it going to be there? So that's a little bit different. That's a difference between tornado watches, warnings, and hurricane watches and warnings. And that's the last slide, I think. Yes. So I'm going to do another one of these soon for chapter 12. But I think from here on out, I'm just going to do one chapter at a time. So that's all for today.